we are going to see the principles of radar interferometry. So we already had an introduction to radar so far, but it was for mainly for amplitude applications, and so using the radar intensity. And now we are going to see how you can use another peculiarity of radar images, which is phase. Something that sounds in the beginning more abstract, but it has very concrete applications, as Ramon will explain to you. Ramon Hanssen is one of our main specialists in Europe for radar interferometry. He has been doing that now for decades, I don't know, 30 years, 25 years? 25 years. So he looks young, but he has done it for a long time. And he's a professor at the University of Delft in Holland. Please, Ramon.
Yes, thank you very much, Francesco. Yeah, first of all, thank you for being here. And I don't know you, so maybe I should first tell you something about me, that you know who is standing here. I think I will be standing here for the whole day, so you have to look at me. You have to bear with me for this day. And then I'll ask, I'd like to know a little bit about your background. My name is Ramon Hanssen, and I'm from the Netherlands. I'm a professor there in geodesy and satellite Earth observation at the TU Delft, the University of Technology in Delft. And I lead a group there where a lot of people are working in navigation, so GNSS, optical, remote sensing, laser scanning, so everything related to geodesy. And particularly, I'm focusing in my research on radar interferometry, so using the phase of the SAR signals and trying to kind of find out secrets of the Earth, so what the Earth tries to hide from us. So apart from being a professor, I started a small spin-off company. Well, it was small when I started it in 2007. It's called SkyGeo, and I worked together on both sides in that company and in the university. But when the company grew, I decided to step back and become a chief science officer, as they call it. But that company is now about 40 people. Working over the entire world in the commercial applications, operational applications of InSAR, and so that allows me to show you some applications of what is happening in the operational side of it. So most of it's myself. I'm working on the science side of it, but I can show you some examples. And the practical that we're going to do was also made available by SkyGeo. They had a very nice portal, and that was allowed me to share this with you guys, and that you didn't need to install software. You can use it on your own computers. And apart from that, I'm also a musician. I make music, and I am the father of 2 daughters. And next week I'm going on holidays, so this will be basically my last my last couple of working days. So that's about me. I would like to know about you guys. So could you just raise hands to that? Can I know who I have in front of me? So who of you is from Latvia? Okay. The ones who are not from Latvia, is people from Estonia? Yeah. Lithuania? Great, welcome. Anybody not from the Baltic states? Okay, everybody's from the Baltic states. Great, good. And the second thing is, so who of you are working in academia in the universities? Okay, that's about half. Okay, so and of those people, who of you are students? Okay, and who of you are teachers? Professors? Okay, so that's also a mix. Good. So the others, so the majority is then from Latvia. You're working in either, let's say, governmental organizations or in industry. So how many of you are in governmental organizations? Okay, and in industry? Okay. Oh, you have this is a great mix. Okay, so I guess you have many different interests today. So I hope that I can accommodate that. I have one specific question. Who of you are there people here from the Latvian Geospatial Information Agency? Oh, okay, good. Yeah, so that is, I think, the closest related to geodesy as far as I understood in Latvia. So, okay, interesting. Okay, so I have, of course, in my computer a whole lot of slides, and I will try to. The idea that I had was to guide you a little bit through the concept of interferometry. So, InSAR, in short, SAR interferometry, going from the basics. I thought also to go a little bit deeper into the equations and to see, okay, what kind of things do we really measure? What is the precision? How can we estimate parameters? And then also look at applications, right? What can we do with it? So I had that in mind. I'll try to limit my amount of speakings by once in a while asking you questions. And the other thing I would like to ask, because this is always a peculiar setup with the computers, is that at some point I notice from experience that people are kind of shifting their eyes to the screen, and then I don't know whether you're tuned in anymore or whether you're checking email. So if you can, I'd like to get some eye contact like I do now. So that is really it's motivating and it gives me energy, right? So if everybody's looking at the screen, that's more difficult for me. Last question. So are there any specific things that you would like to know that you think, hey, if I leave this room at the end of the day, we're talking about interferometry, this is the point that I really would like to address? So somebody who would like to say something about that.
It depends on what you will present.
Yes. Okay. So of course I will give you my what I think may be interesting for you, but of course this is my idea. But if you have something in mind, so when I got the invitation from Francesco, we had some communication with some of you, I think with some of the organizers. There was mention of bridges and infrastructure, for example, so the monitoring of that. There was mention of the city area, there was mention of gas storage facilities, right? So I have a couple of those things in the presentation that will be covered anyway. But if there's anybody who would like to add something, then please go ahead. Yes?
Maybe some applications for ground motion, like natural, like landslides and change.
Yeah. Ground motion, and if you talk about ground change, that is also, you mean that, for example, a building is being placed somewhere, or that the land use is changing, or?
No, more like natural use, like let's say erosion, like coastal erosion or something like that.
Yeah. Okay. Great. Yeah. I will cover that.
And maybe about water dams, how it differs ground motions when the storage is full of water and when it's...
Okay, yeah. So the question is about water, water management, dams, water raise, groundwater table?
More about surroundings of water dams.
Sorry?
More about surroundings of water dams.
The surroundings of water dams. Okay, yeah.
It goes when the water levels are changing
I see.
in the storage.
Is that something that you have here in Latvia? So there are dams with...
At least three large dams we have.
Okay, oh, that's interesting. Okay. I'll see if I can touch upon that. I have some examples I think I can show. Yeah. Anything else? Yeah. Land uplift. Yeah. Okay, good. Yeah, good point. Yeah, I'll touch upon that too. Yeah. Yeah, so as you wish.
Not sure if it's applicable, but groundwater and infiltration.
Ground what?
Groundwater and movement of.
Groundwater and movement. Yeah.
So
okay. Yeah. So groundwater variation and how that affects the soil motion. Yeah, I can touch upon that. Is there anybody here who knows? I studied the geography of Latvia a little bit, but so I guess if in terms of the land covered, do you have areas which are sand and clay and peat in here? So are there big sand areas where forests, for example? Yeah, I see people nodding. Okay.
That's you basically described quaternary geology of Latvia.
Yeah.
the main soil of Latvia.
The main soil is sandy.
It's sandy, clay, marly. No, not really marly, but tilly and peaty.
But you have, I think, at least one main river, right? So there may be river clays also there. Is that true?
Yeah, multiple main rivers that are comparable in size, I guess.
Right. And so around the rivers you have clay.
The river sediments.
Yeah, right. And peat?
A lot.
A lot of peat. Okay. So that is similar to the Netherlands, and we also have issues there. Is peat also on the political agenda here in terms of the CO2 that is getting oxidizes?
Yeah.
It is, okay. And subsidence due to peat compaction?
not sure about that.
Not
But,
so much. Okay, okay.
but I guess it's a thing to cover at least.
Yeah, you normally if you have peat and you have the groundwater table a little bit lower, then the organic material gets exposed to oxygen and it decomposes, and that causes CO2 and methane in the atmosphere, but it also causes land subsidence, and that can cause damage to buildings, or so that is also something that happens here. Okay, very interesting. Anybody else wants to say something?
I heard that it was another potential problem is that now you might have to store gas in some areas because of the problem with Russia. Therefore, when you start storing gas under some surfaces, first you don't know if there might be also ground displacement due to that gas storage, and you don't know exactly where it will be. So
Yeah.
and normally it will not be in urban areas, but there will be anyway infrastructures like bridges and highways nearby.
Yeah.
That's what I understood talking with you in the last days.
Yeah, I will talk about that too. Okay, so let's start. I prepared a couple of slide sets with which are very brief, and actually this is a famous picture from. Does anybody know who painted this? Vincent van Gogh. Huh? And this is called the Starry Night, and I think you know, if you're working in the space sector, then it's always, of course, we have Earth observation, but we're also most of these people are also interested in the stars. So I had this picture of the stars here, with a quote from Seneca saying that there is no easy way from the Earth to the stars, right? And actually, what we're doing in astronomy is that we're looking with our instruments at the stars. We don't know what is happening there. But we would like to find out, right? So we have instruments which look with different wavelengths. We're looking at different parts of the radio spectrum. We exploit the fact that the Earth is rotating so that we have different positions and that we can have different geometry. And so this is something that I also like to do. And this is basically my Starry Night, so the Starry Night of Vincent van Gogh. And what we see here are many different stars. So all these little objects have something, like a star has a mass, at a position, it has an age. So basically my challenge is to try to figure out for every dot, for example, like this little dot over here, so to find out what it actually is. And what I will show you in a minute is that the little dots that I put the arrows with here, that they have something very much in common, right? So the question is, how do we investigate this? And in order to look at this, I would like to kind of show you that actually this is not a starry map, but this is a SAR image, right? So what you see here is just what we get if we have more sensitivity to the backscatter of the radar. The radar illuminates a certain area, and we get a signal back. And the more we get back, the more information that is there, right? So similar like in astronomy, that we have more sensitive instruments, we can look further back in space, or we can see more stars. Or the better the instruments we got, the more resolution we got, and the more information we can get from it. Now, if you look at an image like this, and I think you have seen these kind of images during the week, because people have been talking about SAR as a measurement technique. You also know that there is a lot of interpretation that you can attach to this. And these are the typical images that are actually, well, not really very easy, but they are relatively easy to interpret. Why? Because we see structures, right? We see roads over here. We see urban areas. We see agricultural fields. So everybody can basically get an idea of what we're looking at here. The point is that behind this, there is another secret layer that nobody looks at, and that is the phase, right? So basically, you have to imagine such an image like a big matrix. And what you see here is one value, it's depicted in the gray scale, and that is the amplitude of every pixel, every resolution cell in that matrix. But what we get for every resolution cell is a complex number, right? And a complex number has two numbers, right? A real and an imaginary part. How many of you know what the complex numbers are? Okay, good, not so many. So complex numbers are numbers which have basically two elements, a real and valued part and an imaginary part. And most of it would be better known basically if we look at, let me see, if we look at it as in a vector approach. Let me try to See if I can show that. Discard. So complex numbers have a real axis and an imaginary axis. And every point as a complex number is over here, right? So this point has a real valued number and an imaginary valued number. So this is one way we can describe it. So we can have this pair of the real valued number and the imaginary valued number. But we can also describe it with, for example, an arrow. That would be something like this. All right, so now we have the length of this arrow, which is an amplitude, and the phase, which is phi. Right? Now the thing that you just saw, this thing over here, this is only the amplitude, right? So here basically we see only one part of that vector, only the amplitude. We don't see the angle of the vector, but every pixel has an angle, right? I will show you in a minute what that will look like, but basically it's completely random. It's a value between 0 and 360 degrees, and we have no clue what it is, basically. So this is why people have not really been using that other than for making the image itself. Okay, so if we look at this thing over here, so this is my background, the introduction slide, so the points that I was indicating at. Actually, what you see here is that this star, as I showed it in the beginning here, has some kind of other companions over here, over here, over here, over here. And these are actually artifacts from the SAR image. Right? So basically, if we look at this as a starry image, the Starry Night of Vincent van Gogh, or similar like astronomers look up, we're looking down, we have to figure out, okay, some of these points are actually ghosts. They're not really there. This thing is not really there. There's nothing there in the image, or on the ground. This is the main object. And if we want to know what it is, I went there. I was very close to where I live, so I biked over there. And this big reflection is this building. So it's a peculiar building. You see it from the top here because it has this kind of side thing here, and it has a couple of very straight planes, and it has a water level in front. So basically it acts like a very big corner reflector, right? So the radar signal hits the wall, it hits the other wall, it hits the water, and it goes back. So this is why it's so extremely strong in the image. And then you can immediately imagine that if that building would have been oriented a little bit different, it would look different in the image, right? So if you rotate this building a little bit with your eyes in an optical image, you would still recognize it's the same building. If you would do that in a radar image, this point may completely disappear, right? Because similar, like the satellite has a certain viewing geometry. If that changes, it will change the image, right? So we need to be very careful of that. Okay, I already indicated we're working with complex data. So the amplitude and the phase that I was just talking about, and you can write that in this form. So this is the complex number. It has an amplitude. There's this thing here, in the modulus sign, that is how long the arrow is, and it has a phase psi over here. What you see here is the amplitude, and if we look at the phase, so this is again the amplitude, this is of my city where I come from Delft. If we look at the phase, it looks like this. Right? So completely uninterpretable. The values here range from -pi to +pi. We like to look at the angles in radians, but you could also go from 0 to 360 degrees. Or if you like, you could go from 0 cycles to 1 cycle. So this is always the same thing. But in any case, any pixel has a value between -pi and +pi radians. And we don't know what that value is. Okay, maybe here I could already, well, I'll go to this in a minute. Well, no, let's do it right away. So why is it so random, this pixel? Why is every pixel, does it have a completely unimaginable number? Now, let me try to explain that again with a kind of drawing here. Okay, so suppose that we have a certain resolution cell on the ground, right? So every image has pixels, it has a certain size. So let's say this is, let's say 10 by 10 meter. Or let's say maybe 10 by 20 meters. I like that better, because 10 by 20 meters is maybe the size of this classroom, right? So and now we can imagine something. We can use this size of the classroom as our basic, let's say, basic entity. So what we're going to do is we're going to take the roof off of this classroom. We're going to take the walls away, and we are going to stay here. Each one of us, the computers are going to stay. Francesco is going to stay. He's going to keep on WhatsApping. I'm going to stay here. Cameras are going to stay. Everything is going to stay, but the roof and everything will be away. So that we will be visible by the satellite. Right? What will a radar wave now do if it interacts with this particular pixel, or this resolution cell? Well, what we could do is try to figure out for each little element in this pixel how it would react. So let's take maybe this computer screen over here. Maybe this is one little reflection. Maybe the computer screen is over here. And so for this screen, I have in this complex valued coordinate system, I have a certain vector. Let's draw that in red over here. Maybe this little vector. That's from that computer screen. Maybe from you, there is also a reflection, and that is stems from the location over here, and it has a different angle. So maybe that is this little vector. Now maybe that big screen there, that's a big thing. So if that big screen has a reflection to the radar, so maybe that will be a very strong reflection. So maybe an arrow like this. Let's make it in red again here. Right? So now you can imagine that if we start adding up all these vectors, we're going to start adding up complex numbers, and we're going to start adding up these the vector in a summation. What we get then is the following. So let's make one nice new overview. So this one here, this particular arrow, I'll start with that one. I'm just going to put it here. Now this arrow over here, it's in the other direction. It's a little bit smaller, so I'm going to put it now maybe here. I can add these vectors. This one here, the big one, I'm going to add that now to it too. This is pointing in the other direction, so here. So if this is one pixel, what I'm going to measure is the summation of all these things together. Let's put that in green. So the summation, I start over here. It would be this vector over here, right? So if you understand this concept, it means that within this single pixel, we have maybe 1,000 of these little vectors, right? The radar wavelength is 5 centimeters. It will interact with everything over here. So the number that we're going to get is the summation of all these little vectors. And if we would change the screen a little bit of one of those positions, and we have a wavelength of 5 centimeters, I will talk about that in a minute, then we're going to change one of those vectors, we're going to rotate it. So it's going to be complete random number that we're going to end up with in the end. Right? Sometimes it will be very strong reflection, sometimes it will be small, but the angle that it has, so the phase that it has here in this direction, so let's call that psi, that angle is completely random. Right? Now this is the reason why we have a completely random picture here in the phase image, right? So in principle, the phase of a SAR image is not useful. It's completely random. Okay. So the topic of today will be SAR interferometry, and so I'm going to teach you why we can still capture information from that image. And the way we do it is that we have repeat pass interferometry. So it means that we use different acquisitions of the satellite in different times. So this is the first pass. The satellite looks at the Earth, and it sees a particular pixel, for example, over here. Then maybe 6 days later, if this Sentinel-1A, Sentinel-1B comes, or 12 days later, Sentinel-1A comes again, and it will look at the Earth again. It will see the same pixel. We'll do all kinds of tricks to align the pixels, but suppose that this pixel has now moved down. It has subsided with 5 millimeters or so. Then we're going to see this. Right? We can measure that difference as a fraction of the wavelength. So basically, we're getting down to about 0.5 millimeter precision, sigma. Okay, that's the idea. Now, a little bit of history. So when this came up, when the first satellites were launched, CSAT was the first satellite where it was applied. And then when ESA launched ERS-1, which was, let's say, the main real big Earth observation satellite for ESA, doing interferometry was one of the key things. It was not in the design of the satellite, but people thought, okay, if we are able to do this would be very, very cool. And the waiting was for a big event. And what happened was a big event, was an earthquake in Landers in California. So what you see here is a picture, so-called interferogram, where we see phase indicated with colors. So going from 0 to 360 degrees would be the same as going from red to yellow to blue, and then back to red again, right? So this is what we call one cycle, and our jargon is one fringe. A fringe is one cycle in this pattern. So you could see these kind of images, like if you want to count how old a tree is, you cut the tree and you count the year rings, right? Every year has a certain ring. Here you could do the same thing. So we start counting and we say, okay, 1, 2, 3, 4, maybe, I don't know, maybe 25 of those cycles. Let me see. Let's go up again. Can you guys pull this, make this big again? I'm sure, probably it's the screen here that I touched. Anyway, I'll continue my story, you can do it later. So this was the first time that an earthquake was captured in this way, and that we could see for this whole area, which is tens of kilometers wide and long, we could see the internal deformation due to an earthquake. And you have to remember how spectacular that was, because an earthquake normally happens somewhere, right? You're completely shocked by it, literally and figuratively. But if you want to do a measurement there, then you should have made a measurement before it happened and compare that with a measurement after. And normally you cannot do that, right? So basically what we can do with interferometry is that we have satellite image in an archive, so we simply keep on acquired data. They're stored at the InSAR computers. And at some point when an earthquake happens, we wait for the next image and compare it with the previous ones. So in that way, we can basically look back in time. That's always what we say, right? So with normal geodetic methods, if you want to make a measurement, you need to do a null survey. So you measure what is the situation now. Then you wait for something to happen, and then you make a measurement again, right? So archives help there. So this was a spectacular development. Then we had the deflation of a volcano which came up, of the Etna volcano in Italy. And again, here you see these color cycles going from 0 to 360 degrees, which in this case were interpreted as ground motion of the volcano. The idea was, if the magma chamber of a volcano, sorry about that, if the magma chamber of a volcano would inflate, there would be pressure in the magma chamber, the whole mountain would go up a little bit, and we would be able to measure that. Okay, let me just log in again. I touched the power button here, unfortunately. Okay. Yeah, there we are again. Right, now that happened again then for remote islands like the Galapagos Islands. So these were all covers of nature, which shows the main impact of these kind of studies with interferometry. This is basically traditional interferometry, where we're using one image before something happened, one image after, and we try to figure it out. So we'll talk later about what we can do nowadays, because basically every day, especially here in Latvia, every day you have a new image, every day you have an acquisition. So currently, if we look at the applications, we can do many different things. So this is a teaser that we used for the Fringe conference last time when it was held online, where we showed the city of Amsterdam. And basically here we don't see these fringes again, but we have already moved beyond fringes, because we are going to look at every single pixel and see how that pixel behaves in time. And we could show the velocity of a pixel, for example, the acceleration, or many different applications of it. And that immediately shows you that there are areas where things are happening, right? So this is what makes it so powerful. There are also nationwide and even European-wide product being made now. So this is the map that we made of the Netherlands. Also here, I can show you, I just put them on the... So this is, let me see, the European ground motion map. Maybe this is something that you've already seen. here, the EGMS, European Ground Motion Service. So this is not what I intended to click at. This one. So there has been a very big European project in which all this information has been made available. So here you see all those little points are now scatterers, the radar reflections, which have a certain time series. And we'll talk about that in a minute also to see what that actually means. We made a similar thing here in the Netherlands. A little bit different concept. So here you see basically in the northern part gas extraction and gas storage, what we'll talk about in a minute. Salt mining, we'll see the peatlands, so also the things that you have over here. And we also see the effects of coal mining in the south here. Now if we would go, for example, to the area of the gas extraction here, so this is over here, we zoom in. And at some zoom level, you will start seeing the individual scatterers, as we call them. So the single points which behave as a single observation. And we can look at time series of them. Let me see. Okay, here we see them. So now you can see, oh, it's coming up. You can see that every single dot here now has a certain meaning, and we can investigate that, for example, by getting the, let's see if that works with my tablet. Should do it with my mouse probably. No, refresh it. Okay, so now we have, for that particular point that I clicked on, we have almost 300 observations in time. So like I said, basically every day we have a new image. And we can see how such a particular point behaves in time, right? And so you can imagine that if for each of those millions of points we have these kind of time series, we can really try to understand this and link it to many different disciplines. So the road engineers, the railways, buildings, nowadays also in the Netherlands people using it if they buy a house, they want to check if the house is stable. Gas extraction companies, electricity companies, geospatial services, so many different organizations are using this kind of data. Okay, just to finish my first introduction off, and then maybe there are some questions. So I want to reflect a little bit before I go really into the theory. Okay, this is all very nice, very impressive, but what can we really do with it? And I tried to put this down. This is a new slide that I made. And I thought, let's use some verbs to describe what we can do with it. Oh yeah, great. Fantastic. Thank you very much. Yeah. So if we describe it with verbs, I put a couple of verbs here, and they have a specific meaning. So measure, of course, right? We have a measuring instrument in the sky. It looks down, so we're collecting data. But basically, what we want to do is estimate parameters, right? I don't want to look at only these colored dots on a map or the points on a time series. It looks nice. You could look at measurements, but basically, what we want to do is estimate parameters. We want to estimate, for example, is there an acceleration? Is there a change in velocity, right? So, for example, for the gas extraction, if you start extracting more gas, then the velocity of the deformation will increase, right? If we have gas storage, then usually gas storages work seasonally. So in the winter, you take gas out of the gas storage. In the summer, you put gas in. So in the summer, you're pumping the land up, and in the winter, you're pumping it out. You're extracting it. So then it doesn't really make sense to show a velocity because the thing is going up and down, right? So then you may want to see the amplitude of the variation. So basically with estimate, I mean that we need to choose which parameters we're interested in. Right? So what we're doing now in Delft is trying, for example, for this oxidation of peat, to really estimate the oxidation parameters of the peat directly from the SAR data. Monitor is a very important one because this means that we really exploit the fact that the satellite is coming over all the time, right? So if you're responsible, some of you are from governmental organizations, if you're responsible for a bridge or from a piece of railway, then it's very nice if you have this kind of portal where you can click on a point and you see what happened several years ago, but you want to know whether something happens now, right? So monitor really means that can we compare the latest image that was acquired yesterday or this morning with all the images before, and can we figure out, did something happen, did something change? And if you have 1 billion of observations, maybe if 1 or 2 of them something happens, you can detect, you can flag it, you can send somebody to that location and check out what is happening. So detecting changes is important, detecting changes in behavior in time, detecting whether a new building is built, whether something is being taken away, and categorize. So what kind of phenomena do we see? What kind of things are happening? So these are the main verbs that I thought would describe it. And then, okay, what can you work with? So of course, the traditional things are the ones that are that I showed on the nature covers, right? Earthquakes, tectonics, volcanoes. This is how InSAR came into the spotlight, because it was all of a sudden possible to see that, and we were not able to see it. But how often does an earthquake happen in Lithuania or Latvia or in Estonia? Probably not that much, right? I guess you also don't have any volcanoes over here, so this is all very nice from a scientific perspective. But in my personal subjective opinion, the main power of InSAR is here, the built environment. That's where we live. That's where all the objects are, right? So this is the thing that we should focus on to maximally exploit the value of these systems. I will be talking about what I call geo-objects. So very often we're looking at the surface of the Earth, which is changing, like subsidence, but it's also the objects on it, right? The radar will give us the reflection from the top of this building, from maybe the chimney on this building, but also a reflection from the roof, from the street next door. So for example, if you have soft soils and the street goes down and the building has a good piles, then the difference between that point on top and the point on the ground will tell you very accurately how the street is moving relative to the building, right? And if the building has, for example, utility pipes, like a gas connection, maybe there's a pipe somewhere here under the ground to a gas tube, and the street is subsiding relative to the building, there will be tension on that, it may break, and you may have dangerous situations. So for example, in the Netherlands, the situation is such that we still have, of course, millions of kilometers of gas lines, but there are still 700 kilometers of brittle cast iron gas pipes in the Netherlands, and they are able to replace about 25 kilometers per year. I don't know the situation here, but that is a big problem. And we have had explosions because of differential motion of the street relative to the house, which made these cast iron pipes break, the gas came out, and there was an explosion. So what we're doing now is we're checking all those locations, all those 700 kilometers where we have the brittle cast iron gas pipes, and checking for differential motion between the building and the street next to it, right? So this is the type of intelligence that you can get from it. Past, present, and future is a key word, right? So I already said we can look back in time. Simply, we have an archive. The ERS-1 goes back to 1992, Sentinel to 2015. There are many other satellites also in space now. There will be more. There are commercial satellites which are coming up. So the past is important. The present is very important for monitoring what is happening now. Most of the people in industry or in governmental organizations have management tasks. They are responsible for an asset. So you want to know what is happening right now. And the future is important because we can adapt. We can do things if we know what is happening based on a long time series. Then what do we really measure? What can we do with it? What do we measure? We're measuring position in a way. So for each of those scatterers, we're measuring position. But it's always a very, very tricky thing to do because if we have a GPS antenna, then we know where that antenna is. There's a benchmark somewhere. We can touch that benchmark and we can say, hey, this is the point that I'm measuring. For those of you knowledgeable about leveling, for example, measuring height differences, then we also have bolts in the wall. It's a thing that we can touch, right? With InSAR, we cannot touch anything. We don't know. We get a reflection from this building, maybe. You will have the chance to look at this building later on today with radar eyes. But we don't know exactly where that point is. So we get a position, without knowing actually what it is. But what we do know is that if next time that we look, we're looking at the same position, right? So we're getting these positions, maybe with a precision of meters, maybe decimeters. But most important, we get changes in position, and that we get into millimeter level precision. And then finally, if I start with these verbs to see what can we do with it, is so if we can do all these things, what the most important thing practically, so that is going from the technique to really applications, is we can anticipate. We can think, okay, if the street moves with 3 millimeter per year relative to the building, then over 10 years, 3 centimeters, over 20 years, it's 6 centimeters, right? So we can anticipate for a pipe or for a bridge or for a railway that at some point in time, if that rate continues, things are gonna break, right? In the whole of the Western world, so I think also here in Latvia, we have aging infrastructure. It's one of the big problems of the Western world, right? A lot of buildings have been constructed after the Second World War, so they are maybe 60, 70, 80 years old right now. A lot of bridges have that age, and so all that infrastructure is aging, and it doesn't have an eternal life, right? So we have, over all these countries, especially in Europe, we have all this infrastructure which needs to be replaced, and we cannot change every bridge now. So we need to do that step by step. So one thing you need to do is to monitor each of those assets and see where the damage can happen first, right? And then you start with that piece of asset. If you look at the US, the state of the civil infrastructure in the United States is horrible, right? So the bridges, railways, roads, really very bad state. So if you do these measurements, you can anticipate where will things go wrong. Then you can respond, right? If we look at the present, so we see something changing over time, we can do something about it. We can make planning. We can save resources. We can save lives even, right? So this is the big picture. And again, so why should we do this continuously? Why should also InSAR continue with getting the sentinels up there? Because of knowledge. Knowledge we can anticipate. So this is a statement from EU documents. So better planning leads to substantial cost saving and risk aversion. So that's thing. So knowledge is the first thing we need, and then we can anticipate. And if we can detect, then we can respond, right? Especially for this built environment. If there's structural failure, then usually structural failure is preceded by strain. If something breaks, there's always some tension before, right? So if this building would have a crack in the wall, there's already some little bit of elastic motion that is happening now before the crack will appear. So if you detect the strain, you will be able to respond before the damage happens. Okay, this was my big general introduction before we dive into the equation. So let's have a short break. Are there any questions about this? Yes?
In the map, I can see some dots like next to the bridges, but not on the bridges. Are those meant to be for the bridges themselves?
Yeah, very good, very good observation. So indeed, like I said, the position of those of the points of where we put them also on the map with InSAR, that is not always that perfect. The best thing we can do is with X-band satellites. So for example, the German TerraSAR-X data set or the Italian Cosmos Skyme data set. There we have basically the best positioning precision. So that means if we have such a scatter, we detect the scatter still in the radar coordinate system, the radar frame, but then we have to compute where is that point in the real world, right? And that is actually difficult. So it's uncertain. So that means that if you put, for example, Google Maps or Bing Maps or whatever beneath, it can be that the point will not be as you keep on zooming in exactly on that spot, right? So this is also why courses like this are important, because you need to understand that. So the fact that a point is maybe next to the bridge does not mean that it comes from that part, right? Next to the bridge may be water, right? And it doesn't work over water. But if you understand, okay, so there's a bit of uncertainty, then you can still interpret that point as being from the bridge, right? So it's a very important thing. So we can measure millimeters in terms of deformation, but we don't know exactly where that point is. That's a very funny thing. Yeah. Other questions? Are there any questions about the first part still that came up? No? Okay, so then to start with InSAR, Is my microphone on again? Yeah. So to start with InSAR, I would like to first give you an intuitive approach, and then later on we go into the details. But this is a way to basically to get a feeling of how InSAR works. So I made a couple of sketches with what is important. So in principle, what we have here is the situation where we have an antenna on a satellite flying. This antenna would be left-looking. Most antennas are right-looking for radar satellites. And we basically have two coordinate systems. Let me see if I can use it. This is my pen over here. Oh, no. Where is the pen? Here. Or I can use the laser pointer here. So two coordinate systems. So one is range, and the other one is azimuth, right? So the flying direction of the satellite is called azimuth, and the direction of the pulse is called range. So here you can see that the satellite is emitting pulses, like if you would be having a flashlight in the night, and you would kind of switch it on and then off and then on and off. So you would get these kind of little packages of photons flying through space, and they would interact here on the ground and reflect. Right, so that is basically the standard geometry that we have. Range and azimuth. Okay, then if we look at particularly the range, then that has a certain distance here from the satellite to a certain pixel on the ground. I call that R for a range. And it also has a certain angle here, which we call the look angle. So the angle from the satellite down to the Earth. That range is now expressed in meters, but we cannot really measure it that well. Actually, we measure the range, actually we derive the range by counting time. So we have a clock, we switch it on when the pulse is leaving the antenna, it's traveling through space, so maybe 800 kilometers down, 900 kilometers down, hitting the Earth, and then 900 kilometers back, and we simply record when it is coming back. Right? Then we have an indication of the range, which is not so good, but it's pretty good. But at the same time, as I was indicating, so we also have phase, right? We also have we don't measure the time. The time is just recorded. We measure a complex number. So that means that if this pixel would be very bright, it would have a very white pixel in the image, a long vector, as I indicated. And the distance here from the satellite to the pixel and back can also be expressed in these number of cycles. So how many times did we go from 0 to 360 degrees and back? And that will be millions of times, right? So, and we cannot really count how many, right? So we don't know how many cycles there are. The only thing that we can recall is the fractional phase, as we call it, over here. So we will measure satellite signal coming here to the pixel, going back, and what we're measuring, if this is 0 degrees, this is 180 degrees, so this is maybe 290 degrees or so, right? So the thing that we measure is 290 degrees. So we know that we're somewhere here in this cycle, and we don't know n, which is several millions of full cycles. Again, you have to imagine, for Sentinel, we have a wavelength of 5.6 centimeters, and the distance is maybe 850, 900 kilometers. Right? So millions of cycles will be in that whole path, and I'm only measuring the last part, so the fractional phase, as we call it. Okay, let's keep that in mind. So let's now then have a look at this intuitive feel for what does it do. So we have the satellite. I've drawn it over here, flying. This is the Earth. And if a satellite would now emit a signal, you could see that signal as like a stone if you throw a stone in a pond, and you see the ripples of the waves going by, right? So from here, these circles would expand to the outside. And every circle would be one full cycle, right? That's how we could count it. Obviously, the radar is only looking in this direction, so we don't have any signal here, right? So we have a very narrow beam over here. But in principle, we could see this as a point source with ripples going in all directions. Okay, so now if we have a second satellite, that also will have the same pattern. But as you can already see in this picture, there will be interference. There will be places here where you see this more black and where it's more white. That is, if you throw two stones in the pond, you will see these kind of patterns occurring. And this is the pattern that we're going to use. And we'll come back to this in better animation in a minute, but this is the basic picture, right? So now you can imagine that if these two satellites are further apart or close together, this whole pattern will change. Let me see if I have that. So this is what we call the baseline, the distance between the two satellites. So if it's shorter here, then you see that we have less of these cycles. And if I go back, the previous one, here it was more of them, right? So the farther the satellites are separated, the narrower these fringes are. And this influences our sensitivity to elevation. So if we want to measure the elevation of this hill relative to the ground over here, then we prefer to have satellites far apart from each other, because then we have very high sensitivity. If they're very close to each other, we have only a few of those bands. Okay. Now, there are different systems. So this is the first one is the circles is a circular system. What we see here is a hyperbolic system. So all the points which have the same phase difference, we're measuring the phase as part of the cycle. Two satellites, we are subtracting them from each other. The phase difference that we get then follows this hyperbola. So all points which are on this hyperbola have the same phase difference. Make sure, let's see whether that we can get that straight. Again. All right, so if we have a point over here and a point over here, then this distance here, this is the difference in range, right? Now, if I have a point which is maybe over here, it may have exactly the same difference in distance, right? And so all these points which have the same difference in distance are following this hyperbola. And there's also a hyperbola over here, and a hyperbola over here, and a hyperbola over here. So in the old navigational systems with Lorentz C, before GPS was there, positioning worked like this. Okay. Okay, so here we have the hyperbola again. Now, of course, what happens here is that this pattern, what I'm describing here, is a pattern in space, right? And we have no observation in space. We cannot observe it. We only observe something on the ground. So if you look at the intersection between this pattern here with the ground, then we're going to get values here along the ground, and that is what I tried to indicate over here. So from minus pi to plus pi, 0 to 360 degrees, we have a phase which is going up, then it reaches plus pi, same as 360 degrees, then it doesn't go to 361, but it goes to 0 again, right? So back over here, 0 degrees to 360, 0 degrees to 360, or minus pi to plus pi. So this is the whole pattern that we're going to get for all these different hyperbolas that we have in space. Now the next thing is what we can do is, if the satellites are flying into the board over here, then this would be just one line, one matrix column, for example. And this pattern, we can now give that a color, right? So if it's plus pi, we make it red. If it's minus pi, we make it blue. And if it's 0, we make it yellow, right? So then we get a color scale to indicate this. And that gives us pictures like this here. So now we see a real picture of an interferogram, so a radar interferometry image. And if you look closely on your screen, you will see that there is this pattern over here from red, yellow, blue, red, yellow, blue. So for every line, we have this pattern. If we zoom in, you can see it even better. Right? So here is this whole pattern of fringes, color cycles, for this particular area. This was in Iceland, I think, somewhere. You can also see that these fringes are not completely... So the big picture that you see here is basically due to the curvature of the Earth, right? That is causing this diagonal pattern. And the deviations from it, so the fact where it is somewhere, it is not perfectly aligned, that indicates topography. So we can use that to see how high the mountain is. Okay, so we have this baseline as an important concept. Satellite at time t1, satellite at time t2. We're looking at the Earth. It's so far away that we can assume that these things are parallel. So the baseline is the distance between those two satellite positions. But we can express it in two different ways, or three different ways actually, just like a length and an angle. That's what I'm going to use in the next part. We can look at the horizontal and the vertical one. But more importantly, we can look at it as a perpendicular component and a parallel component. So parallel to the look direction and orthogonal to the look direction. And this is convenient because this number, the perpendicular baseline, this is what is the key thing for measuring topography. So in the equations that I will show you later, if you will see a B with this little symbol, it means that that is the orthogonal component of the baseline, orthogonal to the viewing geometry. Okay, so again, intuitive approach. So I try to do this here in PowerPoint. So I have the two satellites. I have a point on Earth, and let's assume that the Earth is a perfect ellipsoid. There's no topography, maybe even a sphere, right? But well, let's do the ellipsoid. And I gave all the cycles here a different color. So blue for the first one, red, green, purple. Here I have my baseline, the perpendicular baseline. And what I'm going to show you here is the delta r, the distance difference that follows this hyperbolic pattern. So the question is, what is going to happen if I'm going from this point, from here to there? What is going to happen and what are we going to see? Let's have a look. Okay, first part here, we're now in the red part of this cycle, so I call this red over here. Next part, we're moving to the green. Doesn't really, then we're moving to the purple. Let's see, step by step. Purple. Until we're here. Right, I didn't draw all the intermediate stages, but you can imagine what happens. So this distance difference, if we go from here to there, increases. But because we're looking at a wavelength, we're kind of crossing the different wavelengths over here. So going from minus pi to plus pi, we have one full cycle, another full cycle, and another cycle. Now the key thing is that this pattern that I'm having here, I can predict this perfectly. Why? Well, because I know the positions of my satellite. InSAR tracks the position of each satellite. So I can just get that from the orbit files. And the ellipsoid is just a mathematical surface, right? So it's easy. I can predict perfectly what this pattern is going to be. However, there is topography, right? So the real Earth is not an ellipsoid. There are mountains, there are valleys. So what is going to happen is that this topography, this signal that is on top of this, is going to add something to this perfectly mathematical signal. And that's how we do it. So we're subtracting, we're first measuring this. We see all the different cycles. And then we're subtracting the ellipsoid, which we can compute, and the difference is then the elevation. So again, so here you see an example of this reference phase, as we call it, so the phase due to the curved Earth. You see there is no influence of topography over here. We show the amplitude here in the back, and the colors are is the phase. So this is basically the Earth if it would be an ellipsoid. So then we look at the real observations. This was this reference. The real observations do have variation over here, right? So there's all kind of little variations in the pattern. Now, if I subtract this mathematical pattern from the observations, then I get what is called the topographic phase. And this now allows me to compute, to say that this is a mountain, and it has a certain elevation, and I compute how high that elevation is. I can make a DEM, a digital elevation model, of this part of the Earth. Right, so these are the type of pictures that you see if you look at an interferogram showing topography. That's it. Yeah? This is the intuitive approach, to get a bit of feel what is happening. Okay, for everybody, yeah?
You mentioned at the beginning that the phase is random, but is it real random or is it based on physics?
Excellent question, yeah. So, I'll get into that in a minute, but since you asked the question now, let's discuss it now. Okay, so I gave you the example of this classroom being 1 pixel, right? Where we said, okay, the roof is off, satellites looks at this, we get all these little vectors, they are added, and I get one random vector as a result, right? Now the question is, what would happen if we would all kind of not move, everybody freeze, the roof is still off. We wait until the satellite comes back, right? Satellite looks at the same picture. So what do you think the satellite will see? The same, right? So the satellite is, let's assume it's exactly at the same spot. So if we don't move, then this pixel doesn't change, right? Now if we then subtract the two values from each other, what do we get? 0, because it's exactly the same. That is the key, right? So, and 0 is predictable, right? So if nothing changes, and I have two images in subsequent images, nothing changes, the difference is meaningful, right? It's the same as if I give you the number 5, and I give you the number 7, right? And I ask you, okay, add a random value. I give you you say a random value. So you remember 5, you remember 7. You give me a random number. 6. Huh? 6, okay. Now, that random number I don't know, but you have 5 plus 6, he had 7 plus 6. If we subtract the difference, we're going to get 5 minus 7, right? And the 6 is eliminated. That's the key. So that means that if I have billions of pixels, which I do in my SAR image, for a lot of them, things will change. Think about water, right? The sea, right? It is within a second the sea surface changes and the satellite will see something completely different. So no way that I'm going to be able to compare that. Think about a forest, maybe. Think about maybe very dense crop like corn or so. This will change over time, and that means that those pixels will I need to throw them away. I cannot do something with it. But on the other hand, look at a house, look at a road, a railway, a bridge, whatever. So this hard infrastructure, that essentially is the same, right? So that means that even though the phase in the single SAR image is random, if I subtract two images from each other, I get something which makes sense. Right? That's the key. That's why it works. And so maybe for an urban environment, maybe 1% of all the pixels is good. For 1% of all the pixels, it means that it will stay the same in the way that it reflects. That is still, if you have millions of points, 1% is still, 1 million points, 10,000 points is 1%. So this is why, even though we are losing a lot of pixels that we cannot really use, there's still quite a lot there that we can use. Right? And the other thing you can also already think of is that, again, with this example of this classroom being 1 pixel, is that if everybody freezes, right, we do not move, and one person moves, what do you think is going to happen? Yeah, it will change a little bit, but it will be pretty much the same, right? So we can deal with a little bit of variation. It doesn't need to be completely the same. A little bit of noise is okay, as long as most of it is good. So and this is very tricky because this is every square meter on Earth is different. There's no square meter which is the same, right? So every pixel in a SAR image is different. So it's also sometimes difficult to predict whether a pixel will be good or not. But what we do know statistically is that if you're in an urban environment, you have thousands of pixels per square kilometer, right? But there is a certain degree of opportunity in there. It's opportunistic, right? It could be that you want to measure, you have your house and you want to sell your house, you want to know something of your house, and maybe from that particular Sentinel-1 viewing geometry, there's no good pixel on your house because of the interaction with the garden or with the street, whatever. And so you cannot guarantee that you're going to get a picture, a measurement at a particular location, but you can guarantee that in an urban environment, you're going to get 1,000 pixels per square kilometer or so. Make sense? Yeah? Okay, shall we immediately continue? And then we do the, how are we with time? What time is it? Okay, so let me we do the hard part before the coffee, okay? Let me see, because I wanted to really go through the equations.
Did you explain already what means the palette of colors?
The what?
The palette of the colors in the interferometry.
Yes, the fringes, yeah.
Yeah, because it's not always trivial.
Yeah.
Let's see that for the
Yeah, so the question from Francesco is what the colors mean. So the colors are, like I said, these are the fringes, and every color cycle is a phase cycle, from 0 to 360 degrees. So if yellow is 0 degrees, then we get here yellow, purple, blue, green, and back to yellow. That is one full cycle. And like I explained, in this case, this is related to topography. Okay.
It's nothing to do with the colors that you've seen so far in the rest of the course, of course.
No. Yeah, very good. Okay. Number 3. Deriving the equations. Okay, so there are a couple of concepts that are important. So we distinguish a cross-track InSAR. Sometimes people call that XTY, a cross-track InSAR, cross-track interferometry. And that could be in a single pass acquisition, so that the two satellites are flying next to each other at the same time. So they're acquiring the thing at the same time. We can do that also from an airplane, if the two antennas. There has been a space shuttle mission which had two antennas. There is the Terra X and Tandem X, a German mission which had two satellites flying at the same time. So we call that a cross-track InSAR, and this is what you need if you want to measure topography. And the other thing is repeat pass InSAR. That is if there's time in between the two acquisitions. So we're having a satellite acquisition, we wait until the satellite comes back, and then we have another one. And of course, in this case, we have time. In this case, there's no time difference. So if we are talking about deformation, we will not get it here, because here the two images are at the same time. Okay, so this is the thing that I already started with, just to get the overview. I already showed you this to you. Okay, now I'll talk you through the basic concept of the equations. And so you can either try to really completely follow it, or look at the big picture and just trust me in what I do. So we have a satellite in the sky and a pixel on the ground, P, and we want to know, first of all, the height, the elevation of this pixel above some kind of reference height. Let's call it the ellipsoid. So, okay, the distance between the satellite antenna and the pixel, I call that R, or R1. Satellite, I'm going to have an R2 in a minute. And that distance has to be traveled twice, right? So one way to the pixel, and then the signal has to go back. So basically, I have 2 times R1 as the distance that the satellite should, the signal should travel. Now I can measure that in 2 different ways, either in meters or in radians or in degrees. So as a unit, so normally we would express this range in meters, but my principal unit here is a wavelength. The satellite has, the sensor has a wavelength of 5.6 centimeters for C-band, or 3 centimeters for X-band, or 24 centimeters for L-band. Depends, but let's talk about Sentinel here now. So let's say 5.6 centimeters. So I can express this range, 2R1, forth and back, as a certain number times that wavelength, right? So, I don't know, 2,000 kilometers divided by 5.6 centimeters. That is how many times this wavelength fits into the range. However, the thing that I measure is a phase. So this lambda is equivalent to 2 pi, or 360 degrees. So I can also measure this whole distance as the total number of phases that I have. So 3,760 radians divided by 2 pi radians. That is the same kind of fraction. Okay, if we put that in the equation, I get this here. On the left-hand side, the distance in meters divided by the wavelength in meters. So this is a dimensionless unit over here. On the right-hand side, the phase in radians for many, many times the full cycle divided by 2 pi radians. This is radians divided by radians is also dimensionless. Right? This is the key equation. If you understand this, this is where we start. Because here we can say, okay, the lambda we know. We know which sensor we're using. 2 is just a number. 2 pi is also just a number. So basically, I'm relating the phase to a distance over here. So if I want to write my observations here on the left-hand side, psi1, then this is related to the distance. And the minus sign is just something that comes from the data processing. So you can ignore that for a minute. Okay, so this is how the phase, the observed phase, that particular pixel that we have over here, is related to the range. But this is the absolute phase, right? It's not a number between 0 and 2 pi. It is maybe 650 pi, right? So it is an absolute thing. Then we're going to get the second satellite up there, T2. It comes again. And we're going to measure the distance. Now, the satellite will not be exactly in the same position at the time. The orbits drift due to the power of the sun and due to gravitational forces. So it will be a little bit different, and there will be a baseline in between them. And now the distance from this one to the pixel is now 2 times r2. So I can write down the same equations in the same way. So the phase observation for this pixel at this satellite will be psi2, and will be related to distance 2, r2. Now, I already indicated we write this as complex numbers. So basically, the phase here ends up in the exponent over here, and this is just the amplitude, how much I get back from the how much signal I get back from this particular pixel. So what I do in the software is basically complex multiplication. So there are not so many of you who are working with complex numbers, so you can ignore this for a minute, but basically we're multiplying the two complex numbers. That means that we're multiplying the amplitudes. If this is a strong amplitude, we will square it basically, because two acquisitions, same pixel. But it means that the differences, the phases will be different. So we have psi1 minus psi2 over here. So that means if we multiply the two complex images, we get a phase difference. Okay, let's give that phase difference over here a new name. So I use always psi for a single image and phi for the interferogram or the difference. So then if I subtract these two from each other, I get minus 4 pi divided by lambda times delta r. Okay, so where I am now at this time is that if I have the two images, I subtract the phases from each other, I get a difference phase. That this difference phase is related to delta r. And where is delta r? Delta r is here. It's a difference in distance. Right, so this is the geometry that I'm dealing with. So far, so good, right? So now we have the relation between the phase, the thing that I measure, and the unknown, which is delta r. Right? So if I measure something here, I can get delta r. Okay. Now I'm going to do one thing to make the things a little bit easier. I know that this distance is maybe only a couple of 100 meters, and this distance will be maybe 1,000 kilometers. So basically, instead of this geometry, I can use what is called the far field approximation. So going from this situation here, where I have this circle, this is delta r. In fact, in principle, I'm looking parallel. Right? This angle is very, very small. And this makes my geometry easier, because now I have triangles over here. Let's indicate that. So we have the baseline between the two satellites, the delta r, the distance over here. Okay, so now I have pretty good geometry. I also have the perpendicular baseline here that I was talking about, orthogonal to the viewing geometry. And basically, we're having now this whole situation. Okay, so in the previous slide, I ended up here. Observations, unknowns. So now I can express this delta r here with this triangle. I know the baseline, and I know the angles. So basically, if I have a little change in the delta r, if this gets a little bit bigger or smaller, it will change my phi. So I just take the first derivative of that. Now I need the look angle here, so under which angle am I looking? And this is the principal thing that I don't know. I don't know, the radar measures distance. It cannot really measure this angle very well. So the psi, I don't really know. But I can measure a very small change in the angle. That's the key. So if we have this delta r, I can describe that with this triangle, so the b and then the sine of this angle, theta minus alpha, which is the orientation of the baseline. Okay, so I can insert this over here, and then I get a new equation, and I can get the derivative of that. So the derivative of this change, so the delta r is a difference, and it changes depending on where I am, is expressed over here. Go a little bit quicker over here. And basically, if that allows me to measure this little difference in angle. That is the key thing that I'm missing. So I want to have the angle here to the ellipsoid. This is mathematics. I can just compute this. But the true pixel is at a certain elevation. Now that means that there is a little difference in angle, the delta theta. And the whole exercise that I did here is to relate the delta theta to an elevation h over here. So this is the elevation of this point above the ellipsoid. So that is now the key equation. Okay, so if you couldn't follow the whole thing, then just look at the result. So what we have, the left-hand side is the unknown. This is the elevation that I would like to have. Here is an observation phi. This is the number that I get from my image, from the interferogram. And here in between is the wavelength, I know that. The R1 to the ellipsoid, I know that. The sine theta 0, which is also to the ellipsoid, I know that too. 4 pi, I know that, and the perpendicular baseline, I know that too. So this whole factor here in front, this number, is something that I know, and therefore I can go from my observation to my unknown elevation. Yeah? Actually, so what you can see derived from this is, so all these numbers are fixed, so whereas the satellite, the lambda, this is all fixed, except the distance of the satellites. That can differ, because the satellites drift. Sometimes it's very close to 0, so for NVSAT it could be up to 1 kilometer at the perpendicular baseline. For Sentinel actually it's very, very small. But what you can see here is that the topographic phase is inversely scaled by the perpendicular baseline. So what does that mean? It means that if I have a large separation, then I have very good sensitivity to topography. If I have 0 separation between the satellites, I have no sensitivity to topography. Right? Compare this with if you're maybe you did this as a kid, right? If you would close one eye and you try to put your fingers together, this is difficult because you miss parallax, right? If you have 2 eyes, this is why your brain can kind of make you touch the 2 fingers, right? Your 2 eyes have different positions. Your brain does the processing over here, and this is how you can, with 2 eyes, you can touch your fingers, right? With 1 eye, if you have 2 eyes on the same position, it would be more difficult, right? Okay, so I have this also in a different explanation with a little bit of different figures, just to get it across. Again, the same situation, 2 satellites, topography over here, and what we do now is we put the baseline over here, this orientation of the baseline, we get that from the satellite positions, we have the perpendicular baseline, the distance, and the delta R that I was indicating. So the phase of one image is this, the phase of the second image is that. The interferogram is a difference in the phases for each pixel, and that gives me an elevation. So the key thing is that if I want to have this elevation of the point, I know the position of the satellite, I know the range, this is the thing that I need to know. So the phase gives distance differences. So here we have, again, like I threw it with I showed it with a stone in the pond. We have these cycles going away from this satellite, circles. Then we have, for this satellite, also circles. If we subtract the 2, then we get differences. That is the pattern that I was showing before, right? This is the hyperbolic pattern. Every line here is a hyperbola. So for points which are on the same distance, it means that I have an ambiguity in this direction. So if at a certain range pixel, I could be here, if the color is red or the value is plus pi, for example, it could be here, it could be here, it could be anywhere over there. This is the look angle, this is the range, and the azimuth direction is in this plane. So if you combine that, so that means that if I have the ellipsoid over here, the lower part, then and I measure a certain phase, so suppose that I'm for the ellipsoid I would measure this phase, so the let's say the blue color, but in reality I would measure yellow. And the difference in between those 2 colors, the difference in phase, that is what gives me the sensitivity to elevation. Okay. Oh, sorry. Yeah, so that is the big picture, let's say, on how we can measure elevation. And again, I showed you this before. We have observations, we subtract the ellipsoidal Earth, and then we get topography. And now from these equations, we can also compute how high is this mountain. We now can compute the amount of fringes, but we can compute how high is it. And for that, we need this concept of the height ambiguity. So this was the equation that I showed you before, the elevation of a point, the observation that we get, and all these numbers before. So now you could imagine that a very valuable number is, okay, how much is the elevation difference? Oh, sorry. Yeah. How much is the elevation difference between purple here and purple here? So that is the height ambiguity. How much height in meters do we have in 2 pi phase change? So this was the equation. If I put here the value 2 pi, so this value would be 2 pi, I put that over here. Then I have 2 pi divided by 4 pi, that would be the 2 over here. So this number is the height ambiguity. That is, if I look at an interferogram, how many meters are there between one full cycle in phase? You can see that if this baseline gets very, very large, the perpendicular baseline, then the height ambiguity gets very small. So I have very sensitive to elevation. If the perpendicular baseline is small, so the satellites are close to each other, my height ambiguity goes up, and between 2 cycles, I have a very big height difference. So I have not so much sensitivity. So in this picture, it is the same as looking at the difference between, let's say, blue over here and blue over here. So in the range direction. So this is 2 points on the same range. This is the height ambiguity. If the 2 satellites would be closer to each other or further apart, I have more cycles, and the height ambiguity for 2 points in the same range is smaller. Right, so the big picture is this distance between the satellite matters in terms of the topography sensitivity. Okay, let's cut this out. This is a basic message for Sentinel. So if we have Sentinel-1, when the mission was designed, there was a choice on, okay, so how much do we let the orbits drift? I'm not sure if somebody already discussed this in the earlier in the lectures, but so the satellite is being put in a certain orbit, and you try to keep it there, right? Because you would always like to see the Earth from the same perspective in space. But because of solar pressure and gravitational acceleration, the orbits drift. So this is why these satellites have little thrusters, as they call it, little rockets on board. So if the satellite is supposed to fly here, and now after a couple of weeks it's flying here, and they fire the thrusters with a little bit of cooled gas, and it's slowly going to drift back to the nominal orbit. And actually it's going to drift further, and all the way until it's here too far out. And then they will fire the thrusters again, and then it goes back. So basically, it's like a drunk driver on the road, right? It's trying to keep the zigzagging, but trying to stay on the road. Now, this range in which you can go, you can decide. You can say, well, I'm going to let it drift for 1 kilometer, and then I'm going to steer. Or you can say, well, I'm going to already steer much faster. The consequence, of course, if you have a satellite and a very big antenna and you fire the thrusters, the whole thing is going to wiggle, right? Because it's like if you pull the brake in your car, you know there are accelerations, so you don't want to fire these thrusters too much. So here the choice was made to have a maximum baseline of 100 meters. So if this is the nominal orbit where you want the satellite to be, if it drifts over 100 meters, you fire the thrusters and go back to minus 100 meters, and the zigzagging is limited to this range. Right, so I think I'm going to stop for a break here, but so what you could do as a back of envelope calculation is try to compute the height ambiguity for Sentinel-1. Right, so if we're having a baseline of 100 meters, that is this number here, and let's say for the incidence angle here you can use 35 degrees. The wavelength here is 5.6 centimeters, and the range, well, maybe you can take 900 kilometers or so. So if you do that, you can compute the height ambiguity for Sentinel-1. Then the question is this now a good thing or a bad thing? Okay, given time, 10:15, I think this is a good moment to have a coffee break, right? Yeah. But before we break up, so I think a 15-minute break would be good, but are there any questions about this so far? Yep.
I have a question. So, the issue of backs, right? So you have multiple reflections reflected back of the satellite, and I was wondering, what do you know on which one to focus on? Either that arrives first, or do you take the average, or is that kind of uncertainty that you take into account?
Right. So the question is, you get many different reflections coming back, and how do you distinguish what comes from where, right? Okay, yeah, good question. So the one thing is easy, that is time, right? So these reflections will come back at different time intervals. So we know that all the reflections which come from a certain time interval come from a little band at the same range, right? So that is, but then I still don't know where in that band it is. So the second thing is in the azimuth direction, and that we do that by focusing the image. So basically, I always explain it like this. So suppose that I am the satellite, and this is my satellite beam here, and you are the target, right? So I fly by, and now you're entering the target. So I get sent all kinds of pulses. You're still in there until here, and now he's leaving the target, leaving the beam. So what is the difference between all these pulses? The difference is that the distance is changing, right? Because as I fly by, you get closer until you have what we call that the zero Doppler. It's a Doppler shift basically. Yeah? So you have a positive Doppler. You're coming towards me. Now the zero Doppler, because there's no difference in distance here, distance change, and here you're going away. So basically, we're following this Doppler curve, and we can exploit that. So in all these pulses, the phase will be a little bit different because the distance is different. And because we know where points are on Earth, we know where the Earth's surface is, we can kind of focus everything back in the data processing to that particular point. Right? In most of the cases, that goes well. For the example that I showed you in the beginning of this little building, you know, remember, that has ghosts, right? That is where it didn't go well, because actually this antenna also has side lobes, so there's also a little bit of sensitivity there and there. So as long as the reflection is not so extremely strong, it's okay. But that particular building was accidentally so strong that it was also picked up by another one. So in those cases, you get errors. And but in most cases, this is how you can distinguish single scatterers, and then you can position them in the radar image, and consequently, you can position them on the ground in latitude and longitude. Right. So it's basically the SAR focusing algorithm that does that. Another question?
Another question would be, I mean, I guess it will be addressed a bit later, but what is the limit until which the height ambiguity is worse if the baseline increases?
Yeah, also, you guys are also asking very, very good questions. Indeed, there is a difference, there's a limit. Huh? So you can also imagine that, because if I'm looking from that side to this building, I will see a reflection from this wall. But if I would look from that side, I will see something completely different. The other side of the building looks different. So there is actually a very narrow range in which things are still comparable. And we call that the critical baseline. There's a whole signal processing part of that, so I'll let you first have coffee. But the basic thing is that, say, for Sentinel, that would be maybe a couple of kilometers, right? So if the baseline is a couple of kilometers, at some point we start losing points. Flat areas, we lose that faster than point sources. So this is why we steer that satellite to be very close to the nominal orbit, so only the 100-meter orbital tube. Because the longer the orbits are, the more sensitivity, that's good, but it also introduces noise. So the answer to your question is a couple of kilometers in general, for L-band, maybe even a little bit more. But you have to imagine, you can do the back of the envelope calculation. So if the distance is, let's say, 1,000 kilometers, right? And suppose that I have a critical baseline of 1 kilometer, so that means that the angle is 1/1,000 radians, right? So 1/1,000 radians, so one radian is, let's say, 60 degrees. So 1/10 is 6 degrees, 1/100 is 0.6 degrees, so 0.06 degrees in difference. So the 1 kilometer in space sounds like a lot, but it's 0.6 degrees, so it's practically the same. But then already we lose it. If that's more than that, things start to change. Yeah?
In theory, then you should get as close to the critical baseline as you can, right?
If your goal is to do topography. Yeah, right. So this is, after the break, I'm going to talk about motion. This is the key thing, right? So topography, actually, if you want to do it here for Latvia, it would be you would better do it with a laser scanner or so from an airplane. You get much better results. So it was used, if you want to make a DEM for the whole world, then it's great because you can use satellites. But you're not going to get the precision that you need here, for example. The key thing is in the deformation. That's my cliffhanger for after the coffee. Yeah, okay, see you in 15 minutes.